All right, so in the first section, we want to talk about the observations that suggest a chemical reaction has taken place. And again, guys, to some degree, this stuff on some levels is going to be some review because this drives a lot of what your lab work has been up to this point. I want to be able to list 3 requirements for a correctly written chemical equation, and be able to write a word equation and a formula equation for a given chemical reaction, and balance a formula equation by inspection. So here we're getting to dealing with balanced equations. So by definition, guys, a chemical reaction is the process by which one or more substances are changed into one or more different substances. Even as, guys, as I have talked about this in class, a chemical reaction is when you start with one thing and you end up with something completely different. In any chemical reaction, the original substances are known as the reactants, and the resulting substances are known as the products. So obviously there are some key terms here and definitions that you want to be looking at. And when we're working on chemical reactions, we apply the law of conservation of mass. The total mass of reactants must equal the total mass of products for any given chemical equation. So that what that is telling us in mathematical terms is that we lose nothing. Okay, the amount or mass of what you start with is going to be equal to the amount or mass of what you end with, even though they may now be different things. What a chemical equation is, it actually represents symbolically and through formulas the identities and relative molecular or molar amounts of the reactants and products. So remember again, the reactants are what you start with, products are what you end up with. So as an example, we can see the following chemical equation shows us that the reactant ammonium dichromate yields nitrogen, chromium 3 oxide, and water. And we see this here. It's ammonium dichromate on the left, and on the right, when that is broken down or decomposed, you get nitrogen, you get chromium 3 oxide, and you get water. So what are some of the things we look at to indicate a chemical reaction has taken place? There are some easily observed things that happen or changes that take place indicate a chemical reaction has occurred. The first is an evolution of energy as heat or light. So whenever energy is given off as heat or light, that's a pretty good indicator that a chemical reaction has taken place. If a gas is produced, that is a pretty good indication that a chemical reaction has taken place. If a precipitate forms, that is an indication that a chemical reaction has taken place. And as you learned in your labs, a precipitate is solid that's produced as a result of chemical reaction solution and separates or falls down to the bottom. That's what we call precipitate. A color change also is a pretty good indication that a chemical reaction has taken place. So what are the characteristics of chemical equations? Think about these as requirements or rules, and they'll help in writing and reading chemical equations correctly. The equation must represent known facts, so it must be showing you something that is known. It must contain the correct formulas for the reactants and products. The law of conservation of mass must be satisfied. That drives us into the realm of balancing equations. A coefficient, which again you've started to learn, is a small whole number that appears in front of a formula in a chemical equation. That's telling you how many molecules of that thing are present. So this, to start this off, we think about the elements that normally exist as diatomic. And this chart shows us that hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine are normally diatomic molecules, meaning they always exist as 2 atoms bonded together. Most of those are gas, Bromine will exist as a liquid, and iodine will exist as a solid. All right, let's look at word and formula equations. The first step in writing a chemical equation is to identify the facts to be represented. So what happened in the reaction, that's what you're identifying in the equation. Word equation is an equation in which the reactants and products in a chemical reaction are represented by words. So a word equation is qualitative. I tell you, water decomposes into hydrogen and oxygen. That's a word equation. It's qualitative. There's no data points. So methane plus oxygen yields carbon dioxide plus water. That's a word equation. Again, that's qualitative. The next step in writing a correct chemical equation is to replace the names of the reactants and products with appropriate symbols and formulas. So that gets us to what we call a formula equation, which represents the reactants and products of chemical reaction by their symbols or formulas. So an example, the formula equation for the reaction of methane and oxygen would be what you have in the bottom there. CH4 as a gas plus O2 as a gas yields CO2 as a gas plus H2O as a gas. That's with little g's, but this is not necessarily balanced. That's just converting what was written in words into formulas. Next, what we do, we complete this by writing the correct equation in terms of applying the law of conservation of mass to the equation. What that means is that the relative amounts of reactants and products must be equal. So you're going to need to put in numbers. This is where the coefficients come in to make sure that everything's equal. What you have on the left side of the equation equals what you have on the right side of the equation. The process is called balancing equation. It is carried out by inserting coefficients, as I said. So what we do to balance an equation, we count the atoms of elements that are combined with atoms of other elements, and that appear only once on each side of the equation. So there's our not balanced. Notice the 2 that's been added in. We're counting the atoms. Count the carbon atoms. Carbon is already balanced. So you count the carbon atoms, you have 1 on the left side of the arrow and 1 on the right. 2 additional hydrogen atoms are needed on the right side of the equation because you've got 4 hydrogen atoms on the left side, but only 2 on the right until you add in that 2 coefficient. But that's partially balanced because once you add that 2 coefficient to the H2O, you actually then change the number of oxygen. Right? So you consider the number of oxygen atoms, and you need to increase the number of oxygen atoms on the left side to 4 by placing the coefficient 2 in front of the molecular formula for oxygen. So the correct chemical equation, or the balanced formula equation for the burning of methane and oxygen, is CH4 plus 2O2 yields CO2 plus 2H2O. We also need to make sure that we understand all the symbols. The arrow is yields. Arrows going in both directions shows that it's a reversible reaction. S, solid state, down arrow is alternative to S, but it indicates a precipitate. The L is liquid state, AQ, a reactant or product in an aqueous solution dissolved in water. G is gaseous state. Up arrow is the alternative to G, but used only to indicate gaseous product. We can show where we add heat. We can show pressure, temperature, even catalysts by showing the formula. Lots of other symbols. You're just going to need to go through and make sure that you memorize all these symbols so that you know what they mean. This just shows you through diagrammatic what happens in burning methane in a Bunsen burner with oxygen. Now what a sample problem would look like, write word and formula equations for the chemical reaction that occurs when solid sodium oxide is added to water at room temperature and forms sodium hydroxide, which is dissolved in water. Include symbols for physical states in the formula equation. Then balance the formula equation to give a balanced chemical equation. So the word equation must show the reactants, sodium oxide and water, to the left of the arrow. The product, sodium hydroxide, must appear to the right of the arrow. So there's your word equation. Sodium oxide plus water yields sodium hydroxide. Sodium has an oxidation state of +1. That oxygen usually has an oxidation state of -2. And that a hydroxide ion has a charge of -1. So the unbalanced formula equation is Na2O plus H2O yields NaOH. But again, that is not balanced. You add symbols for the physical states of the reactants and products. The coefficient 2 in front of NaOH produces a balanced chemical equation, which looks like this. Na2O, which is a solid, plus H2O liquid, yields 2NaOH, which is aqueous. Another sample problem, translate following chemical equation into a sentence. So you're given that. This is going to be testing your ability to name these. Given the formula, aqueous solutions of barium chloride and sodium chromate react to produce a precipitate of barium chromate plus sodium chloride in aqueous solution. That's taking that chemical balanced equation with the chemical formula and putting it into a sentence in words. So, significance of chemical equations. Quantitative information revealed by a chemical equation includes coefficients of a chemical reaction indicate relative, not absolute, amounts of reactants and products, but it's still a data point. That's quantitative. 1 molecule of hydrogen to 1 molecule of chlorine to 2 molecules of hydrochloric acid. The ratio shows the smallest possible relative amounts of the reactions, reactants, and products. Relative masses of the reactants and products of a chemical equation can be determined from the reactions coefficients. This, of course, we can apply to the math we've already done. An amount of an element or compound in moles can be converted to a mass in grams by multiplying the appropriate molar mass. And that should be familiar. We can also interpret the chemical equation in terms of understanding this in terms of grams. The reverse reaction for a chemical equation has the same relative amounts of substances as the forward reaction. An equation gives no indication of whether a reaction will actually occur. Chemical equations give no information about the speed at which reactions occur. Equations do not give any information about how the bonding between atoms or ions changes during the reaction. To balance chemical equations, we can use the following procedure. This is what we call the inspection, which is a step-by-step approach, the inspection method. Identify the names of the reactants and the products, write a word equation. Water yields hydrogen plus oxygen. Write the formula equation by substituting correct formulas for the names of the reactants and the products. H2OL yields H2 as a gas, NO2 as a gas. Balance the formula equation according to the law of conservation of mass. Balance different types of atoms one at a time. First, balance the atoms of elements that are combined and that appear only once on each side of the equation. Balance polyatomic ions that appear on both sides of the equation as single units. Balance hydrogen atoms and oxygen atoms after atoms of all other elements have been balanced. You balance the formula equation according to the law of conservation of mass. Balance oxygen atoms by increasing the number of H2O molecules. 2H2O yields H2 plus O2. Balance the hydrogen atoms by placing the coefficient 2 in front of the hydrogen. So now you end up with 2H2O yields 2H2 plus O2. Count atoms to be sure that the equation is balanced. You see that it is. Coefficients do not represent smallest possible whole number ratio. Divide the coefficients by their greatest common factor in order to obtain the smallest possible whole number coefficient. Sample problem here, reaction of zinc with aqueous hydrochloric acid produces a solution of zinc chloride and hydrogen gas. Write a balanced chemical equation for the reaction. Write the word equation, zinc plus hydrochloric acid yields zinc chloride plus hydrogen. Write the formula, Zn plus HCl yields ZnCl2 plus H2. Start adjusting the coefficients. Balance chlorine first because combine on both sides. So 2HCl, there you go. Your Cl is balanced. Count atoms to check balance. Notice you've got one zinc on each side, two hydrogen on each side, two chlorine on each side. Simple problem D. Solid aluminum carbide, Al4C3, reacts with water to produce methane gas and solid aluminum hydroxide. Write a balanced chemical equation for this reaction. The reactants are aluminum carbide and water. The products are methane and aluminum hydroxide. The formula, what you see there, obviously not balanced. Balance the aluminum atoms. This is a partial balance at this point. Balance carbon. Partially balanced now. Balance oxygen. Oxygen, unlike hydrogen, appears only once on each side of the equation. End up with Al4C3, 12H2O, plus 12H2O yields 3CH4 plus 4AlOH3. Hydrogen atoms are balanced. Count atoms to check. Everything checks out. The equation is balanced. All right, now we're going to look at section 2, which is go over types of chemical reactions. Again, in one sense, this is review for you guys based on lab work that you were doing. So we want to be able to define and give general equations for synthesis, decomposition, single displacement, double displacement reactions. Classify a reaction as synthesis, decomposition, single displacement, double displacement, or combustion. List 3 kinds of synthesis reactions and 6 kinds of decomposition reactions. List 4 kinds of single displacement reactions and 3 kinds of double displacement reactions. Predict the products of simple reactions given the reactants. All right, so lots of different ways to classify chemical reactions here, guys. We're going to look at the 5 basic types of reactions, which are synthesis, decomposition, single displacement, double displacement, and combustion reactions. So let's talk about synthesis reactions. This is a composition reaction, is another word that we know it by. This is where we have 2 or more substances combine to form a new substance. That's what synthesis means. You're making something new out of other things that you put together. The general equation that shows a synthesis reaction is A plus X yields AX, where AX is a product that is completely different in new substance from A or X. And A and X can be elements or compounds in this type of reaction. And AX is definitely a compound. Now, we can look at synthesis reactions, and there are reactions of elements with oxygen and sulfur. A simple type of synthesis is the combination of an element with oxygen to produce an oxide. Almost all metals react with oxygens to form oxides. So 2Mg plus O2 yields 2MgO. Right? That's magnesium in that case. So you have group 2 elements react in a similar manner, forming oxides with the formula MO, where M represents the metal. Group 1 metals form oxides with the formula M2O, like with lithium, for example. Group 1 and 2 elements react similarly with sulfur, forming what we call sulfides, formulas M2S and MS. So there's rubidium and sulfur. Barium and sulfur. Nonmetals can undergo synthesis reactions with oxygen to form oxides as well. Sulfur reacts with oxygen to form sulfur dioxide. And that's what that equation would look like. Hydrogen reacts with oxygen to form dihydrogen monoxide, which is also water. We can talk about reactions of metals with halogens. Most metals will react with the group 17 elements, which are the halogens, to form either ionic or covalent compounds. Group 1 metals react with the halogens to form ionic compounds with the formula MX, where M is the metal, X is the halogen. An example would be sodium and chlorine, get you your sodium chloride. Group 2 metals react with the halogens to form ionic compounds with the formula MX2. Example would be magnesium and fluorine. Fluorine is so reactive that it combines with almost all metals. We can also talk about synthesis reactions with oxides. Active metals are highly reactive metals. Oxides of active metals react with water to produce metal hydroxides. So an example would be calcium oxide reacts with water to form calcium hydroxide. The balanced equation would look like that. Many oxides of nonmetals in the upper right portion of the periodic table react with water to produce what we call oxyacids. So SO2 plus H2O yields H2SO3, hydrosulfuric acid. And then you've got certain metal oxides and nonmetal oxides react with each other in synthesis reactions to form salts. CaCO, CaO plus SO2, CaSO3. Next are decomposition reactions. Decomposition, you can think of it basically as the opposite of the synthesis. In decomposition, we have a single compound which undergoes a reaction that produces two or more simpler substances. They're the opposite of synthesis, as I said. They're represented by this general equation. AX yields A plus X, where AX is a compound. A and X can be elements or compounds. We have decomposition of binary compounds. Decomposition of a substance by electric current is called electrolysis. I've mentioned that. Common example of this is decomposition of H2O. Oxides of the less active metals, which are located in the lower center of the periodic table, decompose into their elements when heated. That would look like that. That would be mercury oxide. We can also talk about metal carbonates and their decomposition. Look like that. Decomposition of metal hydroxides. decomposition of metal chlorates. And then the classic decomposition of acids. Certain acids decompose into nonmetal oxides and water. Carbonic acid is unstable and decomposes readily at room temperature to produce carbon dioxide and water. Next will be single displacement reactions. In a single displacement reaction, this is also known as a replacement reaction. One element replaces a similar element in a compound. Many single displacement reactions take place in aqueous solution. Single displacement reactions can be represented by the following general equations. A plus bx yields ax plus b, or y plus bx yields by plus x. A, B, X, and Y are elements. AX, BX, and BY are compounds. So we can talk about displacement of a metal in a compound by another metal. Aluminum is more active than lead. So if we show this here, you're going to see that the aluminum displaces the lead. We can talk about displacement of hydrogen in water by a metal. The most active metals, such as those in group 1, react vigorously with water to produce metal hydroxides and hydrogen. So here is your sodium in water. Very, very vigorous reaction, even explosive. Less active metals, like iron, react with steam to form metal oxide and hydrogen gas, which looks like that. The more active metals react with certain acidic solutions. This is displacement of hydrogen in an acid by a metal. So if you, for example, were to use hydrochloric acid and dilute sulfuric acid, replacing the hydrogen in the acid. The reaction products are a metal compound, a salt, and hydrogen gas. That looks like that in equation form. Then we can talk about displacement of halogens. Fluorine is the most active halogen. It can replace any of the other halogens in their compounds. In group 17, each element can replace any element below it, but not any element above it. And this would look like this in terms of a reaction. There's an equation for that. So on and so forth, noting that Br2 plus KCl, there will be no reaction because that's above it. Next, we can talk about double displacement reactions. In double displacement reactions, the ions of two compounds exchange places in an aqueous solution to form two new compounds. Usually in double displacement, one of the compounds formed is going to be a precipitate, an insoluble gas that bubbles out of the solution, or a molecular compound, usually water. The other compound is often soluble and remains dissolved in the solution. The general equation for these is AX plus BY yields AY plus BX. AX, B, and Y represent ions. AY and BX represent ionic and molecular compounds. Formation of a precipitate. Formation of a precipitate occurs when the cations of one reactant combine with the anions of another reactant to form an insoluble or slightly soluble compound. An example of this would be as follows. Precipitate forms as a result of the very strong attractive forces between the lead cation and the iodine anion. We also have the formation of a gas, as we see here. Formation of water, as we see here. And then finally there are combustion reactions. A substance combines with oxygen, releasing a large amount of energy in the form of light and heat. Combustion of hydrogen would be a classic example. 2 hydrogen plus oxygen yields 2H2O. Also the combustion of propane, which looks like that equation. You can use this key here to help you determine the reaction type if this is helpful to you. How do we identify reactions and predict products? Well, go through these questions. Number 1, is there only one reactant? If the answer is no, go to step 2. If the answer is yes, you have a decomposition reaction. Then you move on to 2. Are the reactants 2 elements or 2 simple compounds? If the answer is no, go to step 3. If the answer is yes, you probably have a synthesis reaction. Question 3, are the reactants oxygen and a hydrocarbon? If the answer is no, go to step 4. If the answer is yes, you have a combustion reaction. And 4, are the reactants an element and a compound other than a hydrocarbon? If the answer is no, go to step 5. If the answer is yes, you probably have a displacement reaction. And 5, are the reactants 2 compounds composed of ions? If the answer is no, go back to step 1 because you might have missed the proper category. If the answer is yes, you probably have a double displacement reaction. All right, very quickly, guys, we won't spend a lot of time on this, but I just want to introduce in Section 3 activity series of elements, explain the significance of an activity series, be able to use an activity series to predict whether a given reaction will occur, what the products will be. Pretty straightforward here. The ability of an element to react is referred to as the element's activity. There's a definition you should know. The more readily an element reacts with other substances, the greater its activity is. An activity series is a list of elements organized according to the ease with which the elements undergo certain chemical reactions. For metals, greater activity means greater ease of loss of electrons to form positive ions. For nonmetals, greater activity means a greater ease of gain of electrons to form negative ions. The order in which the elements are listed is usually determined by single displacement reactions. The most active element is placed at the top in the series. It can replace each of the elements below it from a compound in a single displacement reaction. Activity series are used to help predict whether certain chemical reactions will occur. So if you're given an activity series, you know what element is at the top is the most active. It can replace whatever's below it. Next one down can replace whatever below it. Next one down can replace whatever's below it. But one can never replace what is above it. And they're all based on experiments. So these are experimental data that we determine. So here's the activity of halogens, the activity of metals. Charts can be helpful, but also know the general rule.